Welcome back to CCNA2. I know everybody has been practicing over this break between CCNA1 and CCNA2 and still is great at subnetting and all that jazz. And if you're not, well, please be working on it because it's not going away. Hopefully you were going over some of your basic commands and that kind of thing. If not, well, we're going to jump into this, and there is a little bit of review, so we're lucky there. So chapter 1 is Introduction to Switched Networks, which means this entire chapter is on, I don't know, most of it's on switching. They threw a little bit of design in there, as they do with most of the starting chapters from now on. And so, yeah, remember, I'm going to go over this with my lecture, but make sure you read this because I'm just hitting the basics and what I find important in the chapter, and trying to give you a little bit of my details, but you're going to get a whole lot more out of it if you read it yourself. So, after completing this chapter, you will be able to describe convergence of data, voice, and video in the context of switched networks. Describe a switched network in a small to medium-sized business. Explain the process of frame forwarding in a switched network. Compare a collision domain to a broadcast domain. Yippee. Okay, so what do we have next? Feel free to go over some of that stuff. It's QoS and why we need it or something like that. Alright, so growing complexity of networks. Well, in the past we had all these networks that were separated. Your phone was on its own phone network, and your messaging was on, or your data was on its network, and then your video was on its network. And so what we're doing, as you can see with this pipe, is a converged network is actually putting all of that on our same switches as our data has been going on. And so it allows us to save money because we don't have to build 3 different networks anymore. So I don't know what they're talking about here. Sure. Let's see. Oh, features of a converged network: call control, voice messaging, mobility, automated attendant. Okay. Probably automated attendant. If you guys don't know, that's the only one that doesn't make much sense. You might want to read that. Serves customers faster by routing calls directly to the right department or the individual. So it's combining your server in the same network. Alright. So now Cisco's talking about borderless switched networks. Okay, so a borderless switched network, this is kind of big design. It's what actually chapter 1 of CCNA3 is about. But it's kind of a Cisco branding. You could get certified in Cisco borderless switch networks, and all it really means is no matter where you go, if you're on a mobile device, if you're on a laptop, on the wireless network, if you're at one site, your resources go with you. And so what they're showing you is this large campus, which we have the wide area network, right, the WAN, and it's going to connect different sites. And so what this is a public line that is very expensive to connect remote sites. Another way to do this is the public switch telephone network, this PSTN. And so this is where you would have a T1 or a T3 connecting different sites, which in this WAN we're probably talking more like fiber optics running ATM or MPLS or something like that. And then we have the internet, where we could actually use VPNs or virtual private networks to connect remote sites. Okay, so these two are private, and then this one is, well, as you guys know, the internet is made up of multiple networks, and so we use some tools to secure our traffic if we were to go across there. That's why we see a firewall right here. But anyways, the internet edge, data center and services blocks, these are all features of design. You could go over that in Cisco Certified Design Associate would teach you all about these, but let's see, anything important. We'll just read you this one. The Cisco Borderless Network is built on an infrastructure of scalable and resilient hardware and software. It enables different elements from access switches to wireless access points to work together and allow users to access resources from any place at any time, providing optimization, scalability, and security to collaboration and virtualization. So if you really want the base, and this test will ask you, I believe, some questions on this Cisco Borderless Network, make sure you take a look at this section right here, because this sums it up in one sentence. Alright, what do we have on our second? No, well, feel free to watch that video on your own time. Alright, so as we keep going, so the hierarchy, LAN design. Okay, so inside that borderless architecture, we have this thing called the campus. And so the Cisco Enterprise Campus is either a 3-tier design or a 2-tier. Okay, so we have this core. Alright, and this core is just high-speed switching, expensive devices such as a 6500 series router. And the 6500 series router, all it's going to do is we have a bunch of 10 gig, 40 gig, some high-speed links that switch one building to another building. It's built for multiple buildings. Then our distributions are workhorse, and it's doing accessless. It's where in between the core and the distribution is usually layer 3. Between the distribution and the access is layer 2. So this is just pure switching. And then this is where our routing protocols start, and so this is what's each building or each site would be connecting to the distribution. The distribution would go back to a headquarters of the core. The access is where we're going to have all of our end devices, our computers, our phones, access points, stuff like that. So the access layer, the kind of stuff we have going on there is we probably have some QoS, which is actually happening at the layer 3 at the distribution as well, but we have some real basic QoS at the access. We might have some MAC security, and most certainly we're going to have PoE, or power over Ethernet, right, which is that technology switches have to be able to power a phone or an access point without actually having to run power. Okay, so that's the 3-tier design. Now if we're in a company that's a little smaller or maybe doesn't have the budget, we actually do a collapse core, and that's where all the features of the core are built into the distribution layer. And so as you guys can see, this collapse core, we only have 2 layers instead of 3, and so the distribution, the core distribution layer does everything that the core and distribution does over here, but they're not segmented out. And then they connect to the access. Alright, so when we're designing a network, we want it to be these things right here. So we want it to be hierarchical. Alright? Facilitates understanding the role of each device at every tier, simplifies deployment, operation, and management, and reduces fault domains at every tier. Okay, so if you're asking, what is a fault domain? Okay, so just like we have all sorts of domains, any domain is a group, and so the fault domain is the group that if a device fails, what is it going to take with it? Okay, so modularity allows seamless network expansion and integrated service enablement on an on-demand basis. Okay, so that would probably be that we can grow. Usually when we're talking about modularity, I think of being able to put in, I think of modular switches, which means they're not fixed configuration and we can expand them easily. And so at a design level, I don't know, let me think. I don't know. It would be probably also the ability to scale. They're putting that into modularity, so we're not stuck in a flat network design. We are in this tiered design that allows us to scale as a business grows without ripping everything out and putting new stuff in. Resiliency satisfies user expectations for keeping the network always on, right? So we know resiliency would be our redundancy, and the more wires we put in and the more devices, the more we can guarantee a 99.99% uptime, right? Which is, we're looking for a 99 with 4 nines on the end of it on uptime. And then flexibility allows intelligent traffic load sharing by using all network resources. I guess they're talking about load balancing, and I would guess the routing protocols we're going to learn about where we have redundancy, and maybe we're going to use some of those redundant links to actually share the load at all times. Okay. So here's a Cisco's actual what they are saying about the access layer. So let's see what it says. The access layer represents the network edge, where traffic enters or exits the campus network. Traditionally, the primary function of an access layer switch is to provide network access to the user. Access layer switches connect to the distribution switches, which implement network foundation technologies such as routing, quality of service, and security. To meet network application and end-user demand, the next generation switching platforms now provide more converged, integrated, and intelligent services to various types of endpoints at the network edge. Building intelligence into the access layer switches allows applications to operate on the network more efficiently and securely. Okay. The distribution. So what does the distribution layer do? The distribution layer interfaces between the access layer and the core layer to provide many important functions, including aggregating large-scale wiring closet networks, aggregating Layer 2 broadcast domains, and Layer 3 routing boundaries, providing intelligent switching, routing, and network access policy functions to access the rest of the network, providing high availability through redundant distribution layer switches to end user and equal cost paths to the core, providing differentiated services to various classes of service applications at the edge network. Alright, so now the core layer. The core layer is a network backbone. It connects several layers of the campus network. The core layer serves as the aggregator for all of the other campus blocks and ties the campus together with the rest of the network. The primary purpose of the core layer is to provide fault isolation and high-speed backbone connectivity. Alright, so if we're looking at this, these right here, these stacks of switches, are the access layer. And then right here, this would be a distribution switch. Well, I guess it tells you right there too. And so all these distribution switches tie into the core. And now I would guess, just because we see one, there's probably several distribution switches, because if one goes down, that's a single point of failure. And we are definitely doing that at the core, right? We're going to have, if we're just connected to one switch and that core goes down, everything in the network goes down. But as you can see, this core is connecting all of these different buildings together. Alright? And like I said, on a smaller network, here's our collapse core. It's all designed in one, and we definitely want redundancy on that. Okay. So moving on, feel free to do any of these activities. Okay. So the role of switched networks. Okay, we want quality of service, additional security, support for wireless networking and connectivity, support for new technologies such as IP telephony and mobile services. Okay, so quality of service, I hope you guys kind of remember what that is. Quality of service means that things like phone applications, we set them at a higher QoS, so they they get the network resources before data, because going to a website needs a lot less or data, website, or I don't know, a server, anything you're doing on the data side needs less bandwidth than, say, voice over IP, because when you're talking to someone, you want to hear them. Additional security, well, we're going to talk about that as we go on here, but switches allow us to do layer 2 security. They also, maybe you guys remember that they break up collision domains, and so instead of forwarding all your traffic to everyone, they only forward it to you and wherever it needs to go, and so that would be another layer of security. Support for wireless networking and connectivity. Probably talk about PoE. Also, some switches can actually work as a wireless controller, where instead of programming each access point, a wireless controller looks at all of the access points in the system and programs it on the channel it should be, and sets the radios to enough power that they're not interfering with other people, hopefully. So then we have support for new technologies such as IP telephony and mobile services. I think we'd be talking about PoE and just high data rates at that point. So, form factors. Okay, so switches, they come in some form factors. Alright, so first off, we're going to go over here. We have fixed configuration, and I kind of talked about that. That would be, let's see if we have a picture. So we have a fixed configuration switch, like what most of our switches are in the classroom. And that means they're set at 24 ports or 48 ports. Now, the newer switches do have some modularity about them, as our newer switches, you can pull out a fan and put a new fan in, but that's not what they're talking about. They're talking about mostly port density and that kind of thing. And we could put different modules in there, but it's set at, I don't know, usually 4 small form pluggable modules, which I know you guys all remember are the fiber optic modules. Yeah. And those SFPs look a little something like this, if you've forgotten. Okay. The bigger, wider ones that are legacy were GBICs. Remember that. Alright. So anyhow, back to, that's our fixed configuration. Alright, so now our modular. They'd be like our 65.9s or 4500 series, where we can actually throw an entire new blade into that server, and so we can increase our port size, or we can put more fiber I guess port density. We put more fiber optic cables, and they make e-commerce modules and firewalls and all kinds of things that we can throw into these switches. So that's the difference there. So now we'll back to common business considerations when selecting switching equipment. I think you probably figure the first one out, the cost. What kind of switches can we afford, right? That's probably the most important whenever a business does anything. Then the port density. And so why would we care about the port density? Well, port density is how many ports we have, and so we want to make sure that we have enough ports for the devices we have, and probably if you're spending very much money, you want to make sure you have enough ports for expansion in the future. Power. And so power, this is that PoE thing I was talking about, is now common. It is now common to power access points, IP phones, and even compact switches using power over Ethernet. In addition to PoE considerations, some chassis-based switches support redundant power supplies. Okay, so yeah, redundant power supplies and PoE. And so when we're considering PoE, we also need to consider how many devices we are powering with PoE, because a certain switch can only power so many devices. So if you put too many PoE devices on that switch, randomly they're going to shut off. Reliability, I think that's pretty basic. Port speed, you guys understand that? Frame buffers. Okay, so frame buffers are the ability of the switch to store frames. Is important in a network where there may be congested ports to servers or other areas of the network. So what that's saying is, as we get traffic, we want to make sure we have enough, the buffer is big enough to support all the traffic we're getting, and save it until we're forwarding to these to the data center or the internet or wherever we're going. We want to make sure we're not overloading the switch, because then it's going to start dropping traffic if it can't support the amount of frames it is receiving. Scalability, that's the big one, right? The number of users on a network typically grows over time. Therefore, the switch should provide the opportunity for growth. Yep. Once again, if we're going to pay that money, we want to make sure we don't have to replace it within a year. Okay, and so finally we have, this is another feature of switches, and these are stacking cables. And so stacking cables, what they do is those 4 switches right there are going to virtualize through those stacking cables as one switch. And so this way we can save on IP addresses, and it also means if one switch fails, the other ones pick up, and we can still remote in and have redundant links. If we knock a fiber link out of the top one, hopefully we have a redundant link in the other 3, and so the network doesn't go down because one port went down. Alright. So, on switches, hopefully you guys remember, and I don't know if we've talked about this before, but how switches learn a MAC address is by the source MAC address coming into the switch, and so that's the ingress port, and then it looks in its MAC address table to send to the destination port, and I think that's what this video is going to show you. So let's see what it does. Oh yeah, we got a little packet coming into one, and it's EA, and so EA is actually in port 4, and so it sends it to port 4. Now we're hitting 5 with EE, and EE is port 1, and so it's going to send it to EE. So those were the destinations coming in, and it's learned it from the source. So how do we build this table? This is the source MAC address, and the source MAC address, when it receives a frame, remember we have source and destination. So from the source frames that it has received in the future, it will build its MAC address table to allow it to forward to the destination address. And so that table that I was just talking about, we call it the MAC address table. To see it, you say show MAC address table in the switch, but it's also known as the content address table or the CAM table. Okay, so and what that is going to do is it tells you the port to the MAC address. Okay. Now, hopefully, you guys remember when a switch receives frames. If we have a frame right here coming in, and the destination isn't known, the switch is going to send it's not a broadcast, but it will send out. If it doesn't know where that destination is, it sends out a request to see where that MAC address is out every port except the one it was received. It knows it's not here because it received the destination from here, and so it would send it to 3 and 2 if these were the only 2 on the network. If there was more, it would send out all of them except port 1. So maybe that's what we're gonna see here. Oh, yep. Port 2 was empty. Now that it receives a frame, it's gonna do its MAC address, and it sends it back to the PC1. Alright, so PC1 was looking for, apparently it was sending to PC3. The switch didn't know, and so the switch sends out frames to everyone. It knows it's not on port 1 because it came from there, and so it'll send it out all ports except the one it came out of. And then PC3 replies because it was its MAC address. Now from the source MAC address, the switch populates the MAC address table or the CAM table, and then it sends it to PC1. back to PC1. Okay. So now we're in switch forwarding methods. Alright, so store and forward. This is the most common method. And as this says, a store and forward switch receives the entire frame and computes the CRC. If the CRC is valid, the switch looks up the destination address, which determines the outgoing interface. The frame is then forwarded out the correct port. So what that's saying, hopefully you guys remember, the CRC is the cyclic redundancy check. I think it's redundancy, maybe it's reliability. Anyways, it's checking to make sure the frame wasn't damaged, right? It's checking to make sure we got the right frame, and so it waits for the entire frame to get there and then forward it. And this is what most of our switches are. And so let's see what our video says right here. All those 2960s in class, they're right there. Alright, so it checks the CRC, looks good, bam, right? And so then it's going to send it on. Alright, so now if we were doing fancier switches, so we have cut-through switching. Cut-through switching is more data center switches and mostly just data center switches, and so it would be what we call the Nexus series switch, or the 6509 switches can do this as well, but typically all of our other switches are store and forward in the Cisco world. And so what it's doing is it's not going to calculate that whole thing. We want it super fast, like in a data center or probably a storage network, something like that. It's going to get part of the switch or part of the frame and start forwarding it on without checking whether it was damaged or not. So then we go to here, and so what's nice about store and forward, the error checking, and automatic buffering. Alright, so the automatic buffering, the ingress port buffers the process used by the store and forward switches, provides the flexibility to support any mix of Ethernet speeds. So what it's saying is if we're sending out to a certain port, it starts buffering, and so our ports that connect to other networks, like if it's an access switch, we'll go back to, let's see, we'll go back to here. So these access switches are going to connect to the distribution in some way, and so all these end devices are going to forward to here. And if these are all gig switches, we probably still have a gig link to the distribution layer, and so the buffering happens because, say we have a 24 port gig switch and we have 24 people on there. There's 24 gigs coming to a gig forwarding port, and it can only forward at a certain speed. So waiting for the rest is where that buffering happens. So that would be what it's talking about on buffering. Now on cut-through switching, we have two different mechanisms. Maybe okay. So right here, so we have rapid frame forwarding. As indicated in the figure, switching using cut-through can make forwarding decision as soon as it looked up the destination MAC address of the frame in its MAC address table. The switch does not have to wait for the rest of the frame to enter the ingress port before making a forwarding decision. It's not doing error checking. Alright, so now why would that be bad? What if there is an error? So they came up with a second type. So rapid, that was just rapid. So now fragment free switching is a modification of cut-through switching in which the switch waits for the collision window of 64 bytes to pass before forwarding the frame. Okay, so it's like almost like adding a little bit of error checking, just adding a little more reliability, and that's fragment-free cut-through switching rather than just rapid. So rapid, it just waits for the destination, which if we look here on the destination, we're talking about the first 14 bytes, alright? And so now the fragment-free actually is going to wait for 64 bytes to come before it starts sending it. Alright, so collision domains. I kind of talked about this earlier. So a collision domain, if you guys remember on a hub is also known as a repeater. And remember, a hub does not break up a collision domain. It is just more of a collision domain. A switch, because it doesn't just repeat out everything, it stops collisions. Hubs allow for collisions, switches stop them. Okay, and so if each one of these ports, each switch port is a collision domain. Now there's a broadcast domain. So that broadcast domain would go back to our broadcast of our network. And so broadcast domains are broke up by router interfaces, right? Because each router interface is on a different router port. And so when we do that broadcast, the broadcast domain is where it hits. And so the broadcast would still hit all of these if they're in the same network. But this is no longer a collision domain. So we have one broadcast domain and 3 collision domains. So each switch port, or any port that's going full duplex, so actually a router port can break up it'll have a collision domain between, like, well, for one, because it would probably be connected to this switch. So if it's connected to this switch, it would give us another collision domain. Alright, so here's our broadcast domains. So our broadcast domains, if we're looking here, this is all one network, we assume, unless these guys can't talk to each other. So this is one broadcast domain, this is one broadcast domain. Let's see what they're saying. They're just showing you that it is a broadcast domain. And once again, how would we break that up? By throwing a router in there. Hopefully it's showing us that. Nope. So I guess this is just talking about some features that alleviate congestion. High port density switches leave congestion. Now, they can actually make congestion as well. So why would more ports be good for alleviating congestion? Well, because that means we can have more interfaces going into our network rather than, like, if we just had one, like I said, if we had 24 people running a gig with one connection to the switch, we would probably create congestion. But if we have 2 ports going into the distribution layer, then we have less congestion. So the more ports, the easier it would be to do that. Large frame buffers. The ability to store more or receive frames before having to start dropping them is useful. Well, that makes sense, right? Because if you're going to have to resend all your frames, then it's just wasting network bandwidth. Port speed. The faster our ports, the better it goes, right? 1 gig, 10 gig, 40 gig. If you had some 40 gig ports, if you put a 40 gig port on that 24 port gig port, I mean, no problems, right? Fast internal switching. Having the fast internal forwarding capabilities allow high performance. The method that is used may be fast internal bus or shared memory, which affects the overall performance of the switch. So how it is forwarding out the ports. Low per costs, high density ports cost less. That's what it's saying. You want to get your most bang for the buck by picking the right network devices. Alright, so that was our basic thing. I would suggest you guys do this activity right here, this summary on your basic switch configurations, unless you remember how to do the host name, right? Host name, passwords, all that. Make sure you go over that and get that done. Feel free to do those packet tracer challenges if you want. If you have any questions, please send me an email or put it on in the class discussion somewhere. Thank you and have a great